Alright, morning everyone. Okay, so a few notes before we start. The question ones that you submitted have been marked. You should find your mark on Connect. If you're unhappy with your mark for any reason, please contact Jan. You can find his email on the course website, and he is the person in charge of the questions. Question 2 submission is going to be June 9th, the same day as we have the midterm, but it's going to be midnight at that time, so you have until midnight to submit it. If you haven't already submitted your second question, it would be nice if you can target it so it's coming from after what the deadline for the first question was. So it would be an SQL question. Okay, midterm is going to be on Monday. I'll have an office hour today from 2:30 to 3:30. So please come and see me if you still have any questions. And next week tutorials on June 11th is going to be work on your projects. So feel free to attend any tutorial. Especially would be helpful if you're attending the same tutorial as the other people in your group. Now you know after today's lecture you have enough information to finish your project. Okay, so I urge you to start working on it and get a version of the project ready and working, and then you can and then you can start adding details to it. Okay, but it's important for you to have the actual project in place, so you know there's a connection between your TBMS and your code. Any questions before we start? Okay, thanks for the feedback. Some of the things that you guys are mentioning, tutorials are sometimes rushed. It's only a 1-hour tutorial, and I do understand that sometimes what we have for you is more than an hour, and it's hard to go through all of it. The main reason we have it is that for you to be familiar with that, and we always post solutions afterwards. So even if there is a part of it that we don't actually cover in the tutorial, then you can look at it later yourself with the solution that's being provided to you. Textbook is not used enough, or it's boring. I kind of like the textbook. I feel like it's well written. And we're using a different example compared to the one which is in the textbook. So if you guys would like to see a different example of all the material that's being covered in the class, the textbook is a nice complement because you see a different example. However, I feel like for most of the stuff that we've been covering, the actual slides and what we cover in the class has been enough. But you know, again, textbook is a good resource to look into as well. Sorry, my trackpad is acting a little funny today. I don't know why. 2 midterm is too much, and the pace of the class is fast. Believe it or not, 2 midterms is actually for the benefit of the students, because there's a lot of work for the instructors and the TAs to fill out, especially in the summer course. But we feel like with 2 you will get a better understanding of what the course is like, and it would also help you boost your final grade mark as well. Discussions, I had both suggestions that are too long and too short. Not sure which one to go with. That's why I usually have the clicker going, so I get a good estimate from you guys and when you're done so we can move along. Many of you mentioned that projects are vague or not enough help. I think to some extent I would like to see how you guys tackle a problem yourself, right? So the project is the only part of the course where you actually have the opportunity to use your own creativity to come up with meaningful projects. So the reason why they're vague is for you to have, to say what it is you want to do. And you know, if there's anything that you're not sure about, you can always come and talk to me or the TAs, but I would like to see how you guys think about this, because you guys will be looking for employment soon. And when you're working, you're not always going to be given all the details, and you have to look around and find the right solution yourselves. Not enough help with MySQL. The course is going to move towards MySQL in the next few years, and we're going to move away from Oracle. The summertime is not the best time to do this, because it was already rushed. I wouldn't have felt comfortable moving it myself, especially in 6 weeks. So that's why we're currently having both of them in place. However, all of the TAs are very comfortable with MySQL. So if you have any questions, or there's anything that you can't figure out, how to connect it to your project or how to run queries, come and either see me or the TAs. Although there's no specific tutorial for MySQL, but there are good tutorials both online, and you can also come and see us as well. And lectures are long, tell me about it. Unfortunately, there's not much we can do. We've been having a lot of in-class activities because I know it's really hard to sit down and listen for 2.5 hours. Personally, I would have trouble with that. So, that's why we tried to have a lot of in-class discussions so you wouldn't get bored as much. Also nice to see many of you had some positive comments about the course, so that was really nice. SQL is fantastic. Clicker questions and group discussions were liked by many people. Many of you had positive comments about the group exam and the fact that there are plenty of exercises and past exams that you can look into. And some of you mentioned lectures are fun. Alright, so let's get back to where we ended up last lecture. And I just want to clarify on this. At the end of the previous lecture, there was a question about this on and whether we can use where instead. And so the reason why we're using on here instead of where is because we're using a full outer join. And the syntax that goes with a full outer join is that if you want to go and do your join on attributes which are different from the two tables, then you would need to use the syntax of on. So that on is giving you information about what attributes will be joined from both tables. Okay, so just a clarification on that syntax. Back to SQL. So we've seen simple select from queries, and we've seen union, intersect, and accept. We've seen nested queries. We've seen aggregated functions being used, and then we saw how you can use group by or having clauses as part of your queries as well. And we saw that you can have null, and based on that null, you can also have full outer joins or left outer joins. But everything we've seen so far is all about getting a query about something which is already in your database. But what if you want to modify some of the relations? What if you want to update someone's grade? What if you want to add a new student? What if you want to delete some students? So first of all, we'll look at some of those, and then we'll have a look at assertions and triggers and how we can use those in our databases today. Inserting values into a database is pretty easy. So all you need to do is to say insert into name of your table, student, values, and these are the values that will be inserted into your table. You can also insert with null. So if you want to do that, you say add tuple, and then when you're doing your insert, you can also use null here as well. It's also possible to insert values in a bunch instead of doing it one at a time. And your insert can actually be a select, which is coming from a different table. So for example, let's say I want to enroll a student with student ID 511355593 into every class taught by a specific faculty. Okay, so what I'm going to do is I'm going to say insert into enroll, and this is what I want to be inserted. Select the name of the student, so in that relation all the time, that's going to be, the first attribute is going to have that value. And then name, and then class, and then I have a where condition. Where the where condition says that I want the FID to be the professor's ID. Okay, so what's going to happen here is that, first of all, it's going to run that select command to get a bunch of values, and all those values will then go and be inserted into your enroll table. Sorry, I'm going to start using my mouse. The other thing that you need to be careful about is when you do that select clause, the relation that's being returned with that select clause have to be compatible with the table that you want to insert into. Right? Because when you do a select clause, basically what's going to be returned to you is a relation. So this is what's being returned to you. You need to make sure that this is compatible with the table that you're trying to insert into, because now every tuple in the select clause that you just had is going to be inserted into the relationship that you have. Any questions? You can also delete values from your SQL. Okay, so you can say delete from student where name is Smith, and that's going to go into your student table and it's going to delete all of the tuples that have name Smith. You can also do things like delete from student where age of that student is bigger than the average. And one thing to note about that is that whenever you're doing a delete, first of all, it's going to look at that where clause, it's going to figure out that where clause, and then it's going to delete everything based on that where clause. Because what do you think might happen if it look at each of the tuples separately and then run that where clause only for that tuple? Would anything happen differently if you delete tuple by tuple rather than looking at everything together, the where clause together, and then doing the delete? Anyone? In this example, what would happen if I start at the top of my table, look at the first one, look at their age, and check whether it's higher than the average? If it is, I'm going to delete them. If not, I'm going to keep them in. Then I can move to the second one. And then I can find the average age again and see whether I need to delete this person or not. Would this raise any problems?
The threshold will change for the average age.
The average will change, right? And I've said that the order of tuples in a relation does not matter. So I shouldn't get different values based on the current order that things are stored in my database. If I just look at the first tuple, and currently I check what the average age is, and if this is bigger than the average, if I delete this, then if I move to the second row, if I calculate the average again, now I have a different average. So what's going to happen is that, first of all, the average is going to be calculated based on all of the tuples that you have. That's going to be fixed, and then we're going to look through each of the tuples to see which are the ones that we need to keep and which are the ones that we need to delete. You can also update values. So you can use the update command to say update student and set their age to a new value. Now sometimes you might need to have to do multiple updates. For example, let's say you want to add 2 to the age of everyone, and you want the max to be 100. That means if someone is currently 99, you don't want them to be 101, but you want them to be 100. These are the two updates that you're going to write. The first is going to say, if their age is bigger than 98, then make their age 100. For anyone else, after that, you're going to say, update every age smaller than 98 by 2. Yeah?
Could you change that last part to just where age is less than 100? Because you've already changed all the ages that are 98 to 100. So.
If it's smaller than 100, not including 100, that would work. Right. But what would happen if you switch the order of these two? If you switch the order, someone who's 97 will first turn to be 99 based on the first update that you do, and then the second update will grab him again and make his age 100. So his age will actually move from 97 to 100 and will be incremented by 3. Okay, so you need to ensure that whenever you do an update, whether ordering would matter or not. questions? Alright, let's also talk about integrity constraints again. So we've been using integrity constraints to describe the conditions that every legal instance of our database should have. Okay, so we've talked about whether we should have domain constraints, whether we should have a primary key, what are foreign keys, and we've also had general constraints so far. One way that you can create a constraint is by using a check command for a table. So let's say I have an enroll table, and I'm going to use a constraint number, and I can give this a name, constraint number 15, which says that none of my classes can be held in row R15. Maybe there's a flood there or something, or it's out of order for some reason. So at the bottom of my create table command, I have a check, and that check is going to check that none of my classes are held in that table. You can add a check constraint to a table if the constraint that you have is only going to be an attribute of that specific table. Right? So if the constraint that I have is only about attributes which are within the enroll table, as it is here, I can say I can have this constraint as part of this table. These are going to be the syntax of how you do constraints is quite different from one DBMS to another. So again, that's the main reason why we're going to be testing these mostly on your projects, and it's not going to be part of your exam. Okay, but what this is saying is that select that, and you want to make sure that the value you get here is different to R15. Sometimes it's nice to have constraints just to make sure that someone is not putting in a typo. If I add a constraint that I expect my students to be under 100, assuming that is the case, then it's nice because if someone is putting in their student ID instead of their age, then I can see that they have a big number and this can't really be their age, so I can say, wait, there's a typo here. The value that you have doesn't really correspond to what I'm looking for. So sometimes it's nice to have this sort of constraints to make sure that we're catching typos. We also had constraints that went over multiple relations. And if you remember, when we were talking about this constraint way back, we were saying that you can't really do this right now. This was a many-to-many constraint over a relationship where you have full participation constraint coming from both your entities. So here you're saying that you should have employees and departments fully participating in this relationship. We can't really use the constraint that we just talked about right now in order to add this because this constraint is coming from multiple tables. And I cannot add it into one specific constraint for one table. And this is where we're going to use assertions. Assertions are constraints that can be for multiple tables at the same time. Okay, so I can say I want every employee to work in one department, and I can make a create assertion total employment, which is going to check that there doesn't exist someone that doesn't work in a specific department. And again, both for assertion and constraints, I can have a check, and then I can have an SQL query, and basically what that check is checking to see whether that SQL query, when that runs, is calculated as true. So I want to not exist someone such that this SQL query. Whenever you're creating something new, when you're inserting values, or whenever you're updating values in your database, all the assertions and all the constraints will be checked. So whenever you're doing any modifications that might ruin the current constraints that you have, before actually going and proceeding to the changes that you would like to have, it's going to check whether it's going to be violating any of the rules that you currently have in your database. So if you want to enroll a new person into a course, first that constraint is going to check whether it's going to be in Rule 15 or not. And as long as it's not violating any of your constraints, it will be added. If it is violating some of your current constraints, you're going to get an error back and it's not going to be added to your database. And the same is going to happen to your assertions as well. If currently one department only has one person in it and you want to delete that person, and if that's violating your current constraint that every department needs to have someone, it's going to not allow you to delete that person. Because it says, look, there's a violation because there's a rule that says you can't have a department that there's no one in it. Any questions? But people weren't even happy with that. I mean, they had rules which was avoiding any violations to happen to your database, but people were thinking about active databases. And what people were thinking about is, sometimes I want something to happen automatically if I do something. Okay, so this is what they were thinking about. They were thinking about, if there's an event that happens in my database and some conditions hold, I want some actions to automatically happen to my database. And a few years ago, maybe around 2000, everybody loved to be an active database. All the DBMSs were thinking about, I want to be the first active database. And everybody was rushing into this, so nobody really waited for the triggers and the notation and the syntax for them to be universal through different database management systems. So if you look at triggers, the syntax is really complicated, and it also depends quite a bit on the DBMS that you're using. One thing to note is that triggers may have cascading effect. Let's say you say that if something happens in one table and some conditions hold, then you want something else to happen in another table. So that other thing is going to happen automatically, and that thing that happened automatically may be the rising reason why another trigger will be called. So you might make one change, and that change might cascade over multiple times, because every time the trigger is creating something new, and that something new may be triggering something else. Again, with triggers, we're not going to have them on our exams, but you do need to have them as part of your project. And this is what a trigger could look like. Let's say I want to create a trigger that has name Young Student Update. And basically, let's assume this is what I want to do. Let's assume that I would like to have a separate table apart from my student table, where that table is only keeping students, young students, which are under 19 or something. In reality, this is a really bad idea. Why is this a bad idea? And what would I really need to do if I want to keep this? This is a bad idea because wait a minute, I already have students, so I don't really need to create another table for my young student. In reality, I can use a view which says that that view is only going to be showing me my young students. Okay, so if you really want to implement this, this isn't really a good idea. You can just use a view for that. But let's assume, in order to show how triggers work, let's assume that you want to create a young student table. That whenever you have students which are younger than 18, you also want them to be added to that table. So this trigger says, after you insert into your student table, referencing new table, new students, so whatever you just added right now, let's assume everything that you added right now is in a new table called new student. So let's say you just added 5 new students. So you'll have 5 tuples in your new student table. For each statement, for each of those, insert into young students as long as their age is smaller or equal to 18. So then what this would mean is that whenever I add a student to my student table, it would automatically be added into my young students without me having to do the insert manually. Okay, and there are different combinations of things that you can use. You can say before you insert, you can say after you insert. So there are different operations that you can use instead of basically this template. But generally, this is what a trigger would look like. That trigger would have an event, a condition. Based on that event and condition, some actions will be applied. Any questions? Okay, so with the addition of constraints, assertions, and triggers, you now have enough knowledge to do your projects. Okay, everything in it. So everything we cover in the lecture from now on is not going to really go into your projects. Okay, so that's nice. Now we know how to do SQL. But how can we code with SQL? Direct SQL is rarely used on its own. And as you guys are seeing with your projects, you can't really have a program which is just running on top of your MySQL. And if you're using it with another programming language, for you guys it's going to be either Java or PHP, then there's a mismatch between what it is that you have in your program and what is inside your tables and relations. Okay, so in your programming language, you're talking about variables, values, pointers, an object, and all you have in your SQL, in your DBMS, are relations and tables. And sometimes there's not a one-to-one matching between the variables and the objects that you have in your project, in your program, compared to what you have in your DBMS. And sometimes it's challenging to take all the information from your relations and work with it inside your program. Because of that, there's been a lot of tries to see whether we can combine the two. Whether we can move aside from having relational databases on their own and have them as part of our programming. However, this has never happened. We've had a lot of new programming languages coming and going, but relational algebra and relational databases haven't really been changing much for the last few decades. And a lot of times, many people have found it easier to just use API from any other programming language that you're using in order to interact with a database management system. So you're going to have your program running in some language, and then you're going to interact with using API with a relational database management system. And what you can do is, you can make a connection from that language to your relational database management system, and then you can start asking queries. You ask a query by writing an SQL. You send that to the database. The database is going to look at that SQL. If it's an insertion or a modification, it's going to make the modification to your data. If it's a retrieval of information, it's going to get that inside a table, and it's going to return a result for you. So what you get back is a result set, which is a table that is going to be the answer of the SQL that you sent over. Or it could be an error. For example, if something you wanted to do was there was an error in the SQL, or it was violating some of the integrities that you have in your DBMS. And this is what it will look like. So you can make a connection. You'll have a login and password in order to connect to your database. And then you have a query, and you write the query as a string. And then you can execute that query, and what you're going to get back is a result set. Okay, so you run that, you get a result set, and then you can have a while or a for loop or whatever way that you want to go over that result, and you can look at each of those tuples one by one. And this is nice. This is nice because when you're writing the program, you don't really care as much about the physical layer anymore. You don't care about how that information is stored and who's taking care of that. All you're doing is you're accessing that information inside your program, and the DBMS doesn't really care about what program you're writing. Right? I can have the same UBC database, and I could have multiple different programs working with that, and the database really doesn't care about the programs that's using it. As long as there's a protocol or there's some information that's being shared between the two, and you know the schema and the views that are used inside that relational database, you don't really care about anything else. Now, one thing that we can just finish this chapter off with is, you can see that I'm sending over the login and password. Right? And there are many websites that don't allow you to have the password that you would like. So you have something in mind and it's going to say, no, wait, your password needs to have this in it and it shouldn't have this in it. And have you thought why that is? Yes? Injection. That's exactly the right answer. So here it says, hi, your son in school have been having some trouble, computer trouble. And the mom says, oh dear, did you break something? In a way, did you really name your son Robert Drop Table Students? Oh yeah, little Bobby would call him. And this is what's happening. And well, we lost all of our data for this year. I hope you're happy. And the mom says, well, you should learn to standardize your databases. And basically what's happening is that it's injecting that part of the SQL as part of the username or password or something. And if you're not careful about that, that could be part of the SQL that is going to run on your database without you knowing that it's going to happen. And you might lose all that information. Okay, and finally, let's summarize this chapter. SQL was an important factor in the early acceptance of relational models. And we've looked at SQL in details, in a lot of details. Okay, so there are many learning goals for this chapter. Make sure that you are familiar with all of them for the midterm. Any questions about chapter 5? Alright, so this is as far as the midterm is going to go. Okay, so everything we've covered up to now, except the things that are said which are not going to be on the midterm, this is as far as the midterm is going to be. Next chapter, the stuff we're going to do on Datalog are not going to be part of the midterm. Okay, so deductive databases. What we're doing is coming from chapter 24 of the textbook, parts 1 to section 1 to section 4. There is some theory as part of, I think, section 2. The parts that we don't cover in the lecture, you don't really need to know about. Okay, some of the theory that I haven't covered in the class, and there are in textbook in that sections, you don't need to worry about. Okay, when we last left databases, which was a few minutes ago, we had decided that there were great things. We knew how to conceptually model them in AR diagrams. We know how to logically model them in relational models. We know how to normalize them. And we could run SQL queries on them. We have learned a lot. And now the question is, are there any other ways that we can query that data? So right now we know relational algebra as one language, and we know SQL as another. This is the third and the final one that we're going to look at. And there are some learning goals for the chapter that you can view. And let's start with a motivating example. Let's say I have a table, and this table keeps information about parts, subparts, and number of those subparts that you need to build something. Okay, so for example, to get a trike, you need wheels, you need 3 of them, you need a frame, you need 1 of that, and to get a frame, you need some other stuff. So for a frame, you need a seat, and as you can see, this table is showing this tree. And whatever is inside this tree are all the required components in order to build a track. And now what I want you to do is, with your neighbors, try to come up with a query that gives me all the components required for building a track. And this is surprisingly difficult. Okay, so give it a go.
There could be other stuff.
Oh, you're saying if there was a... But then you'd have to
Go like get all the subparts like and then from that table you get all the subparts for that. Maybe the subparts for that.
Oh, yeah.
You can use your tertiaries.
There's a logical stage.
You have to know the table.
No, you don't use some part. Like, yeah.
How would you make that?
Like, there's going to be other.
No, like you one
just keep
very
on.
That's why it's hard.
Well, but you have to somehow know which one to choose. You have to go through the tree somehow.
Get all the subparts for the trike. And with that, you get all the subparts.
Like, why don't you just try excellent. And then go down to the sections. Like, you go first or something. And then select. I keep it going.
Does anyone have any brilliant ideas? The subpart number? Well, this table could have multiple components for multiple things, right? So if it was only talking about the components that you need for a trike, you could just get the subparts, but you could have subparts which are coming from multiple different objects here.
So eventually just search all of the trike.
That's kind of the right idea. So one suggestion is keep on joining. And how do you join? Let's get 2 copies of this table. So we'll have an A1 copy and we have an A2 copy. Okay, so what I want is that for the A1.subpart, so trike has a wheel and I want that wheel to be the same as A2.part. Okay, so I want A.subpart to be equal to A2.part, and I want A1.part to be trike. So what's that going to give me? That's going to give me trike, but it's only going to go one level down inside that tree. Right? Because right now it's going to look at subparts, and from the subparts it's going to look at the subparts of those subparts. But it's not going to go any lower in that tree. Now if I want the rim and the tube, I need to do one more join. So I need to take this now and I need to join it with A once more in order to get those. But the question is, I don't know how many joins I need to do. How many joins do I need to do in order to get the final answer? One way would be keep on joining until the result that you get doesn't change. Which is kind of what Datalog is going to do later that we're going to see. But really, there's no elegant way for me to write this in SQL. And the reason why there's no elegant way for me to write this in SQL is that I have a recursive function there, which is basically resembling a tree rather than a table. Right? I'm showing it in a table, but really what I mean is a tree. And SQL is generally not good with complex data structures. So this is one of the reasons why we need to look at another language, even though SQL is really strong on many of the questions and queries that we have in mind. Any questions? Yes?
Are you looking for components that's only the child node? If you're looking for child node, if you just list all the parts that has only the subpart, like has a name on subpart but does not have a name on the parts, will that give you all the child?
So, do all the subparts? And then what?
Like we find, like it's not a child node, it will have a name in the subpart as well as in the parts. If it's a child node, it will have only the name on the subpart, but not
Right.
on the
So you're defining this as we'll do in Java or C or a recursive function, right? You're saying, see whether what you have is a parent or does it have any children or not. If it's a child node, then if it's a leaf, then don't go any further. If it's not a leaf, keep going down until you find the rest of the stuff, right? That's what you have in mind?
like I just list all the things that has like a name on the subpart but does not have a name on the parts. Like
List all the things that have a name on the subpart.
I mean,
Maybe the table is misleading. So in this table, I don't just have parts for a trike. I have parts for different things. I have it for cars, I have it for bicycles, I have it for everything, right? So right now I just have parts which are coming from trikes, so I can just look at those subparts. But if I have parts for different objects in there, then this wouldn't work. Does that answer your question? Come and see me if you still have trouble. Right? So I can have different objects in here. And once I have parts and subparts that are coming from different objects, it's not as easy to do this query. Okay, so Datalog is based on a logic notation. Based on Prolog, and it can express queries that are not expressible in relational algebra. Or at least not easily in relational algebra. And these are mostly queries that have some kind of recursion implemented as part of that query. And again, this is built on top of relational algebra. We don't have any grouping by or aggregation here. So there are some things that we don't have in Datalog that we had in SQL, but there are some queries that we can really do better using Datalog compared to SQL. Let's start with a nice and easy example. Okay, so let's say that in our data we have some facts. We know that D likes Jan. We know that Jan likes Jamie. We know that D likes Wally, and we know that Wally likes D. So these are the facts that I have in my data. I can also have rules. So a rule says that loves of A and C, where A and C are variables, comes from likes AB and likes BC. Okay, so how many people are familiar with first order logic? A few. We're not going to get into the details of first order logic here, but this notion of a rule allows me to generate new facts from my database. And this is why we call this a deductive database. Currently, I can have a table, if I'm thinking about this from a relational perspective. I can have a table which is called likes, and it has two attributes, and I can have D and Jan, and I can add these people here. Right? So this gives me a table about people that like each other. Since I have this rule which tells me who loves who, I can create a second table myself with the facts that are coming from the likes table. Okay, so this tells me if I combine three variables, A, B, and C, such that I have likes of A and B. So let's see, I have D and Jan, so I can have A being D, and I can have B being Jan. And then I want to find another tuple where the first value is Jan, because I have already binded my B to Jan. So I need to find a like where I have Jan and someone else. So I have likes of Jan and Jamie. I have found 3 values for A, B, and C for likes of A and B and likes of B, C. These 3 facts together allow me to conclude that A loves C. So D loves Jamie can go as a fact into my love table. Any questions? So my relations are represented by predicates. So I have tuples that are represented by likes of D and Jan. I can also have arithmetic comparison atoms. So I can also have, and we're going to see examples of this soon, I have variables x and y, and I want x and y plus 5 to be bigger than z divided by 2. Okay, so I can have those as part of my rules as well. Or I can have x and I want x to be smaller than 100. I can also have negations, and I can say it is not the case that D loves G or likes G. And not, here is a little different to how we're talking about it in SQL, but here not means that there does not exist a fact which says that D likes G. And this is what our Datalog rules look like. Right? So I have an atom which is defined based on a bunch of different atoms. Atom 1 to atom A. And I'm saying that if all of the facts on the right-hand side of a rule are true, then what's in the head is also true. And this is my reasoning, this is my deduction, that whenever things on the right-hand side of a rule are true, I can infer the thing on the left-hand side. Whenever you have a rule, you have an and between the different atoms or predicates that you have. Okay, so this comma, or it could also be shown as an and, means that I want it to be the case that likes AB and likes BC. I cannot have an or here. This rule is only meaningful if I have an and. And again, you can read this rule as saying, if we know the body, then we know the head. Any questions? Now when I have my fact, I'm talking about constant values. So D, Jan, and Jamie, and Wally, and Jean are constant values in my tables here. And then I have variables in order to define my rules. And to get a new rule like the one I got here, I'm going to have assignment of facts or constants from my data to the variables as part of the body, and based on those assignments, I'm going to generate a new fact which is being added to my list of facts. Okay, so I'm assigning value A to a constant D, B has value Jen, and then C has value Jamie, so that's why I can drive this new fact. Okay, so let's have a running example that we're going to do some queries on. Let's assume that we have product where those products have a product ID, they have a name, they have a price, they have a category, and they have a maker CID, which is the company that they're coming from. We have a purchase table, where the purchase, there's a person who's buying, a buyer, which has a SIN number. There's a seller, which has a SIN number. There's a store where the purchase is coming from. And there's a PID, which is the product which is being bought. And this PID, you can think of this as a foreign key, basically, to the product. We also have a company where that company has an ID, which is similar to the maker CID that we have here. That company has a name, it has a stock price, which is its current stock price, and there's a country that it's coming from. And we have people that have a SIN number, they have a name, they have a phone number, and there's a city that they're from. Now let's see what it would mean to do projection, or some of the other rules that we've had as part of relational algebra or SQL as part of Datalog. Okay, so projection is performed like this. Let's say I want to find the name of all the products. Okay, so in relational algebra that would be look at the product table and return the name. In Datalog, it would be product, and product has values, variables P, N, P, R, C, and M. So that's the PID, that's the name, that's the price, that's the category, and this is the maker. And what I want to be returned is just the N. So I'm making a new predicate, N, where that N is being returned. So now, if you can assume, if I have a bunch of facts which is going from my product table, okay, and one of these attributes is name, then what this rule is returning is a list of all of these values, which is similar to my projection. Any questions? Alright, then I would like you to find the countries of all the companies. And click when you're done. You need to learn it first. Right, feel free to discuss this with your neighbors.
I guess so.
Right? So, if you want to find the country of all the companies, Then you'll have a rule, a fact, an atom, company has CID, has name, has stock price, has country, and what you want to return is just the country. Okay, make sure you don't have C for both of these. Because what would happen if you have the same variable for two of these, then that would mean you want both of these to be the same thing. And that would mean you would like the ID of the company to be similar to the country of the company. Which usually isn't the case. Any questions? Let's look at selection. So, let's assume we want to find all purchases with the same buyer and seller. Okay, so I'm looking for purchases. So again, you can do this similar to how we were doing SQL queries before. First of all, you can look at the relations that you need to consider when you're doing a query. And then you can start thinking about what it is that you want to apply to those relations. And then you can think about what it is that you want to be returned. So you can have that select from where inside your mind when you're doing these queries as well. Okay, so you're looking at purchase. You want the buyer and the seller to have the same value. And any purchase that has the same buyer and the seller, you're returning those as your answer. Okay, so if you have a purchase table where that purchase table have multiple different purchases, what's being returned as your answer for answer 1 here is only those purchases that have the same value both for the buyer and the seller. And if you want to find all the Canadian companies, then you're going to look at company and you want country to have the constant value Canada. I've tried to be consistent and have my variables as capital values and my constants either as being inside quotes or being lowercase. Any questions about any of these? And let's assume that you want to find all products over 99, that amount. And now you can add that also as a restriction, as a constraint to your rule as well. So you can say I want products with variable I to show the PID, N to show the name, P to show the price, C to show the category, and M to show the maker. And I want P, which is the price, to be bigger than 99.99. And if you think from a relational algebra, then you're looking at products and you're doing sigma over price being bigger than 99.99. Alright, then I want you to find all English companies with stock price less than 100. And click when you're done.
You can. We usually go for the mathematical expressions. We put So I'm saying there's a variable P, and then I'm defining later that So how do you want to put it? You say P is bigger than then that would just have a variable which is smaller. We'll take a bunch of variables. It wouldn't make sense because I don't know what's right? If it's rounded to something everybody doesn't know.
All right. So find all English companies with stock price less than 100. I'm looking at companies where the country is England and stock price is smaller than 100. And I'm returning those. So in my answer, everything will have country England. And every stock price here would be the case that it's smaller than 100. A few people are asking, can I keep this as CO as a variable and then say CO equals England? That is allowed in some of the languages that implement Datalog, and some it's not. The main reason why I wouldn't do that here is because I don't really need to have that variable anymore. If it was the case that I needed to do some more comparison on that value with something else as well, then it would be useful for me to have a variable which is country, but I usually only need that whenever I'm doing some arithmetic calculation. So when I have some arithmetic calculations, I can define that as a variable and then later say what are the restrictions on that is. If it's a variable and I want to bind it to a constant, then I'm just going to use that constant instead of that variable. And it wouldn't work if I say s smaller than 100 as instead of my variable s. Again, depending on the language, it might take that as the actual variable. So I would think that the variable is s smaller 100. Yeah?
Instead of having can we also have like CO or something and then make it CO equal?
So instead of having England here have CO and then have CO equals England, that's the first thing I mentioned. So it would make sense, but what are you gaining with that? Some languages that implement this would allow you, some wouldn't. Some would only allow you to have arithmetic expressions out and not constants. Yeah.
Would doing it this way be consistent across all languages?
Yes, this is across all languages.
What if you wanted multiple countries like England and France?
So the question is, what if you wanted to be England, the companies that are both England and France, or you would need an or instead, right? That are coming from either England or France. So would it make sense to have an and? You don't want the company to be both England and France. It would make sense to have it as an or, and we'll cover that in a few slides. Basically what's going to happen is you need two rules to define that. Any other questions? Let's take a 10 minutes break and resume at 22 past.